Hello. In this lecture, we are going to start, in this lecture series rather, we're going to start with complex analysis. And this is certainly an important topic for your mathematics, CSI and NET, and also for people who are studying right now for their masters. So basically, we've already seen a little bit about complex numbers in our previous classes. We'll start from there. So the idea is to start from very basics and lead to the advanced level. Okay. So the target audience is generally masters, all those who are doing their MSc in mathematics, and probably a few students who are interested even, and if they have completed their BSc, they can also get benefited, and people who are preparing for any sort of exams like GATE or NET or something, from them also this particular lecture series will be quite helpful. So the idea is to start from very basics, although there would be areas where I may skip a little bit of derivation or proof, whatever you want to say, and all those proofs or possibly the derivation part you can see in the textbooks. So the textbooks one can follow. If you follow Indian authors, then there are two authors that I may suggest. The A very good book by S. Ponuswamy sir, that is very good. You can actually go through this book. This is, I think, if I'm not wrong, Ponuswamy, I think. Okay. So this is one. If you can buy it, it is from Narosa Publishers. And second, uh, if you really want to get into some Indian authors only, then some people recommend H.S. Kasana also. Although I have seen this book, I have not seen this book. Okay. If you want to follow for some other authors, like foreign authors, and if you are fine with that, for basic, you can go with Churchill. And then if you want to literally go a little bit all the more rigorous, then you can see Alforce. Okay. And if you want a more comprehensive book, then you can follow John B. Conway. So all these are the books I'm recommending you. If you can just take one of them, not all these. Yeah, I think this book will be more than sufficient eh, if you want an exposure till GATE or NET level. But these foreign authors also are quite good. Basic book you can go for Churchill, and also there is another book called as Schaum series. You can find good amount of problem there, so that may help you in your what you can say, doing more and more problems. Okay, so all these things are uh, like these are some things that I wanted to tell you before I head for the things. So the point is this particular course you can I'll go throughout. I'll try my level best to do the proofs also. But if I am not able to do the proofs, then you can certainly see these proofs here. I mean anywhere in these books. So that would help anyhow. Okay. So let us start with complex numbers. So first is complex number. And as you're aware from your standard 11th also, complex numbers are in general what usually people see, like they think that a plus iota b is some complex number. No, b is not a complex number. Complex number is nothing but it is an ordered pair of real number only. So what it is ordered pair of real numbers. Okay. So basically, if I am writing a plus iota b, it means a comma b, whether I write this way or whether I write this way, this is one and the same thing. Here A also belongs to R and B also belongs to R. So none of them is imaginary. Both of them are real only. Iota is attached to B, so therefore we usually call it as imaginary part. So let's say this is your some complex number Z. So imaginary part of Z would be called as B, and real part of Z would be called as A. However, both A and B are real. Don't get mistaken that any of them is imaginary. No, none of them is imaginary. Both of them are real entities only. Okay, so this is first thing. Um, uh, Further, you know that if you see the algebraic structure of algebraic structure of complex numbers, if one sees the algebraic structure of complex numbers, one can say that it follows all the properties of the field. So it forms a field structure. It forms a field structure. Okay, this is an important thing that you can verify by your own self. It's not that difficult. Okay. Another thing is that you can associate every complex number. You can associate every complex number with a point in plane. With point in the plane. Okay. So you can associate any of your complex number with the point in the plane. I think this is clear. Okay. So you can associate with every complex number a point in the plane. I hope till now everything is clear. So basically, if you want to visualize your complex number, so if I say that your complex number is, let's say, 3 plus iota 4, let's say this is your complex number, then you can write it as, you can visualize it in this way. So this will be a 3 comma 4. So for every complex number, you can have a point in the complex plane, or you can say simply plane. Okay, I hope it is clear. Okay, then see, for recognizing any complex number, you need two things. Now, because it is in plane, you require two things. One is the sense of magnitude, and other is the sense of direction. So basically, whenever you are defining a complex number, you need two things. You need the modulus of it, and you also need the argument, or simply the, let's say if I want to explain here, if I'm writing 3 comma 4, so from origin the distance would be simply 5. So this is your mod z. Mod z for a complex number is nothing but it is equals to root over, let's say if the number is z is equal to a plus iota b, then modulus of z is nothing but a square plus b square. Okay, and if I want to write the argument of z, so argument of z will be simply tan inverse of tan inverse of b upon a. I hope it is clear. Okay, just give me a minute. Okay. So sorry. Okay, so for every complex number, you can associate a magnitude of the complex number, and you can also associate a direction, tan inverse b pi. And what actually differs in real analysis, one of the two striking features, if anybody asks you, what are the two striking features which separates, you can say, or you can say, which are different in real analysis and complex analysis. So in real analysis, as long as you were studying your real analysis, you did not have a concept of multi-valued functions. Okay, so in real analysis, for every you can say, for every input, you have a unique output. But here you will have something called as multi-valuedness. Multi-valuedness. Okay, so this is one very different feature from real analysis. That is, you may have functions which are multi-valued in nature. For example, argument itself. So whenever you say argument, you know that tan function is a periodic function. So if I'm writing tan inverse b by a, so argument can be many. Now, in order to restrict this multi-valuedness, you need to define the principal argument. Those are different things, but one thing that separates your real analysis and complex analysis is one thing is multi-valuedness. So in complex analysis, you may talk of multi-valued functions also. However, in real analysis, you do not talk of multi-valuedness. Okay. The second thing that you'll find is that if a function is differentiable here, if a function is once, if you prove that function is once differentiable, then this function is infinitely differentiable on any region R. Let's say if on region R, you find that a function f is differentiable. I'm talking about function of complex variable. If I find that on this region R, this fz is once differentiable, then it becomes infinitely differentiable. And it gives us a scope of writing the power series representation of this particular function. So these two attributes, you can say, uh, uh, these two features are very unique features of complex analysis. Okay, you don't find all these things in real analysis. In real analysis, if function is once differentiable, you cannot talk of the second order derivative also. With all certainty, you cannot say that the second order derivative exists. Example, let's say x modulus of x. So if you see x modulus of x, it is x square if x is greater than equal to 0, and it is minus of x square if x is less than 0. However, if you differentiate this you will get 2x if x is greater than equal to 0 and minus 2x if x is less than 0, which certainly is nothing but 2 times modulus of x. And you know that modulus of x is not differentiable at x equal to 0. So if this is your function, you can define the first order derivative, but you cannot define the second order derivative. So once, if you can define the first order derivative, it does not guarantee the existence of the second order derivative. Example I've given here. But in complex analysis, as I'll go along and I'll teach you further, you would be able to understand that if function is once differentiable, then it opens the scope of infinite differentiability. So these are the two features which are very striking in the complex analysis that you have to pay attention to. Overall, the real number is also a field, complex number also forms a field. That is quite clear. Okay. So this is very much clear that real number forms a field. So and complex number also forms a field. So that way, algebraic structure wise, both of them are fields. So real number also forms a field, and complex numbers also form a field. So for example, if I say that what would be the algebraic structure would be the field structure. And by field structure, I would mean that it will, with respect to addition and multiplication. So let's say I will define addition and multiplication first. So let us define addition. So addition of two complex numbers, you can define, let's say x plus, I'll write in this manner. Okay. So this is simply x plus u and y plus b. And if I define the multiplication, then it will be xu minus vy, comma, xv plus uy. Okay. So this is how you can define the multiplication. So once you define this multiplication and addition, then I can write that C forms a field, forms, I think field structure, forms a field structure with respect to addition and multiplication defined above. So these two definitions I've already given. So it forms a field with respect to the addition and multiplication. Why? Because C, what you can say, it forms an abelian group. It forms an abelian group with respect to the addition, with respect to addition, with 0, 0 being the additive identity. I think this thing you can verify on your own, that the set of complex numbers forms an abelian group with respect to addition, with 0, 0 being the additive identity. And then if a plus iota b is there, then certainly you know that a plus iota b is there, then certainly minus a minus iota b is there. So if you add this up to this, then you will get the identity. So this is the existence of inverse. And you already know that if two complex numbers are added, it will give a complex number. Okay. So all these things you already know. So that I'm not going to elaborate. I'm saying that uh, one thing is clear, that with respect to addition, complex numbers are going to form, um, just with respect to the complex, sorry, with respect to addition, complex numbers are going to form an abelian group, abelian additive group. Okay, so this is something that you know. So I'm not much elaborating there. Secondly, um, the group uh, C star, that implies I'm removing the origin from it. So if I'm talking of the set of set of non-zero complex numbers, then it also forms an abelian group with respect to multiplication. It forms an abelian group with respect to multiplication, under multiplication. And the additive, the multiplicative identity here would be 1 comma 0. So 1 comma 0 would be multiplicative identity. All other things I know you can verify on your own. And additive identity would be 0 comma 0. Okay, so these are two things. Third number, the distributivity holds. So distributivity also holds. Third number is that the distribution also holds. Distributivity. That is, if I say that there are three complex numbers, let's say a plus iota b, you have x plus iota y, and let's say you have another complex number, let's say u plus iota b. Okay, all these things belongs to set of complex numbers. Then one can write a comma b times x comma y plus u comma v is equals to simply a comma b into x comma y, and then you can write a comma b into u comma b. Okay, so you can write this way. So this means that distributivity holds. If all these three properties hold, we say that a structure, the algebraic structure, is the field structure. So this I hope you might know. So this means that your complex numbers forms a field structure. And I've already told you that for every complex number, there is a point in the plane. So in order to understand that, I've already given you an example that if I write 3 plus iota 4, it implies what? It implies the point 3 comma 4. It implies the point 3 comma 4. I hope it is clear. Okay, so we can say that there here you can associate itself with a field, and it is isomorphic to r square over. Okay, so for every complex number, you can find a point in the plane. In the plane means in r square. Okay, so whenever what you can see, another thing, a real number is nothing but it is a special case of a complex number. So real number is nothing but it is a special case of a complex number. So you can associate a real number, or you can associate the real space with x comma 0. So basically, if I'm writing that, if I'm saying that x is a real number, so you can write it as x comma 0. Okay. So basically, you can connect your real numbers with a field isomorphism h x is equal to x comma 0. Okay. So you can identify your set of real numbers with the field isomorphism x comma 0. Okay. So all these things, I think it is clear. Another thing which you will find here is that two complex numbers are said to be equal if their real parts are equal and their imaginary parts are equal. So if I'm saying that two complex numbers are equal, let's say if I'm saying x1 comma y1 is equals to x2 comma y2, then it necessarily implies that x1 should be equals to x2 and y1 should be equal to y2. That is, if I'm saying that z1 and z2 are two complex numbers and they're equal, then their real parts must be equal separately, and their imaginary parts also must be equal. Okay, this is one of the important properties. All these things are standard 11 things, but still I'm educate, just teaching you so that things get in like we start from very basics. This is what is my idea. Okay, so one thing is clear. Now the point is that as you know that real numbers form an ordered field. Real numbers form an ordered field. However, in complex number, you will find that the field of complex number, I would write rather, the field, uh, what I should say, the field of complex numbers cannot be total ordered, cannot be, sorry, cannot be totally ordered. Okay, मतलब uh, in what you can say in consonance with, in consonance or the way you can see the usual orders in with usual order on R. So basically, let's say in real numbers you had this 5 is greater than 3, 3 is greater than 2. All these things are there, like minus 3 is less than minus 2. So all these orderedness is there, but such orderedness doesn't exist in the set of complex number. Only equality exists. So equality I've already stated, but orderedness doesn't exist as such. Are you getting my point? Okay. So generally you may see a little bit of proof for it. Uh, uh, well, I think everything such proofs are given already in the book, but I'm still doing it. Let's say suppose uh, suppose that order exists. You know? Suppose that such ordering exists. Such ordering means like this kind of ordering exists. Ordering exists. And in the set of complex numbers. So let's say if I'm saying some iota is a complex number, then there are possibility that iota would be greater than 0 and iota would be less than 0. Okay. If ordering exists, then there are two possibilities. Either iota would be greater than 0 or iota would be less than 0, since you know that iota certainly is non-zero. You already know what is iota. Iota is a symbol given to this particular number. And this, that's okay. Another thing I will write also. So iota is, I'll write the story of iota also. So iota is certainly non-zero. So you can either associate iota with greater than 0 or you can write it as minus 0. Okay. In any case, you know that minus 1 is nothing but iota into iota. Okay. If you're multiplying the same number with itself, if any such ordering would have existed, then the right hand side would have been greater than 0. However, the left hand side is less than 0. So clearly there is a contradiction. Okay, so this observation is quite important, and this observation clearly shows that any such ordering is impossible in C. Okay, any such ordering is impossible in C. Okay, you may have equality. So equality wise, it is fine. If you want to write that two complex numbers are equal, then it is fine. Then clearly the real entities would be equal to the real entity and the imaginary entity would be equal to the imaginary entity. That is fine. But you cannot have such kind of ordering. Let's say 5 is greater than 3, 3 is greater than 2, minus 3 is less than minus 2. All these things you can say in real numbers. So you might have studied in real analysis that in the real numbers form an ordered field. Okay. Rather you write real numbers form a complete ordered field because there is a property called as completeness. Okay, but here in this the field of complex number, you won't find such kind of orderedness that you've already seen in the uh, set of real numbers. So usual ordering property, uh, like one we find in the set of real numbers, you'll not find in the set of complex numbers. So one thing that you have to uh, at first you have to understand. Okay, so if anybody asks you, this is a very fundamental kind of thing. One should remember a very basic proof. You can find these things in books also, but still I have written so that you are able to get it. So till now, we have only touched upon the numbers part. And I will teach more on the, less on the number side. I'll teach more on the function side. Okay. but still I wanted to do it, so it is fine. Okay, and you also know that why there was a need of finding complex number. So why there is a need of complex number? That also is very clear. See, uh, the inconsistency came because of this particular thing, that is the root over of negative numbers. So you cannot find any real numbers. You cannot find any real number whose root over you cannot find any real number corresponding to the square root of a negative number. Okay, so you know that, let's say if I want to say that if I want to find a solution of x plus 2 equal to 0, let's say in a set of natural number, can I find? I cannot find. I know that x is equal to minus 2 would be solution, and set of natural number doesn't contain a minus of 2. Similarly, if I want to find the solution of 2x minus 1 equal to 0 in set of integers, will I be able to find it? No, I will not be able to find it. Similarly, uh, uh, if I take, let's say, set of rational numbers. Let's say if I take a set of rational numbers, and if I want to find x square minus 2 equal to 0, if I want to find the solution of x square minus 2 in the set of rational number, can I find? No. So similarly, I cannot find any real number whose solution I cannot find any real number corresponding to x squared less than 0. And it necessitates me to define something called as iota, or and this actually leads to the generation of complex numbers. Okay, so I cannot find any real number corresponding to x square plus 1 equal to 0 in R. So I cannot find any solution corresponding to x square plus 1 equal to 0. I cannot find any real solution corresponding to x square plus 1 equal to 0. Is that clear? Okay, now let us come to different sort of representations of the complex number. So first up is your polar representation. So this is from your standard 11th only. So if I say that there is a complex number, let us say x plus iota v, or simply I can write x comma y. So if this is your complex number, then this particular distance is termed as the modulus of this. So modulus of z is nothing but it is equals to a root over x square plus y square. And you know from your standard 11th only that z bar is nothing but the image of the number keeping x-axis as a mirror. So if I take x-axis as a mirror, this particular image here is nothing but it is equals to x minus y. This is nothing but it is the conjugate of z. So corresponding to z, you have a conjugate of z. This conjugate of z this is called as the conjugate of a complex number. This is called as the conjugate of a complex number. Is that clear till now? So it is a conjugate of a complex number. If this is a complex number, that is x comma y, then the conjugate of complex number x comma minus y is nothing but it is the mirror image about this x-axis. Okay, and this particular theta is referred to as the argument of z. Okay, now the problem with argument is that argument is a multi-valued function. It is a multi-valued function. Why it is a multi-valued function? Because you know that the periodicity of tan x or tan theta is pi. So if I write tan inverse 1, it can certainly be equals to pi by 4. It certainly can be equals to 5 pi by 4 also, and all different things. So you need to define something called as the principal argument that we are going to come shortly. But at first you should remember that what is conjugate? Conjugate is z bar. Why I have written conjugate? Because you must understand that modulus of z whole square is nothing but z into z bar. Okay, so z into z bar is what? X plus iota y into x minus iota y, which is certainly equals to what? X square plus y square. And with, so this is how you can write it. Understand this modulus of z is an important concept. Don't confuse it with z square. Z square is a different entity altogether. It is x square minus y square comma 2xy. You can do it on your own also. I'm doing it. Generally, I found students getting confused in this thing. Don't get confused. What is z squared? Z square is x plus iota y square, which is x square minus y square plus 2 iota x square. So clearly understand that mod z whole square and z square are not same. Okay, so mod z whole square is z into z conjugate. Z conjugate is the complex conjugate of the of a complex number. And what is a complex conjugate? It is nothing but it is the mirror image of the complex number about x-axis. I hope it is clear. Now, what happens is, if you do a certain level of mathematics, you know from your standard 12th, that if I want to write a little bit, so this would be what? So this particular projection is nothing, but it is the y coordinate, and this projection is nothing, but it is the x coordinate. So you can also write your z as modulus of z cos of theta plus modulus of z, sorry, iota, modulus of z sin theta. So what I have done, I have only replaced x is equal to r cos theta or simply mod z cos theta, and I have replaced y is equal to mod z sin theta. This is clear from here. I think this thing is quite easy. You can do it on your own. And this particular thing can also be written as modulus of z. If I take common out, this will be cos theta plus iota sin theta, right? And then you can write it as simply modulus of z e to power iota theta. And here theta I am writing as argument of z. So this way you can express your a complex number by the help of the magnitude of a complex number and by the argument of the complex number. Is that clear? Till now everything is clear or not? Because these are very basics. One has to remember. You don't have to forget all these things. Okay. Is that clear till now? आया ना तो बोलो भाई. घटिया सवाल मत पूछना, बाकी सब चलेगा. हाँ सर. चलो ठीक है. Okay. Till now everything is clear. Yes, okay. ठीक है. Okay, done. So.
Yes sir.
Okay.
Sir, इसका proof.
हाँ हाँ.
Sir, इसका proof.
हाँ हाँ वो भी पढ़ेंगे. Don't worry. पहले एक बार just take a look over all these things. Na? Once you just take a look of all these things, we'll understand all group and everything, ring
Sir,
and everything.
last वाला argument of z वाला एक ही power.
क्या जी?
Sir, last वाला है ना z bar वाला.
Okay.
Mod z cos theta iota sin theta.
Okay. So कुछ नहीं है. It is very simple. ये रहा तुम्हारा simply मान लो जैसे mod z. If this is your theta, so ये projection कितना होगा? ये जाएगा mod z cos theta. ये projection क्या होगा? Mod z sin theta. ठीक है. Vector algebra कुछ भी नहीं है. X comma y. If this is your point x comma y, then x would be equals to what? Mod z cos theta. What would be your y? Y would be simply mod z sin theta. So if I write x plus iota y, I can also write it as modulus of z cos theta plus iota modulus of z sin theta. And what you can do is, you can simply expand these two. Sin theta and cos theta series, you know, na? Theta 1 minus theta square upon 2 factorial. If you do this way, na, isko dekho aise karo. You write this way. So this, you write 1 minus theta square upon 2 factorial plus theta raised to power 4 upon 4 factorial. And then you write iota, you write theta, and then minus iota theta upon 3 factorial. Then write plus iota theta upon 5 factorial. Okay. And so on and so forth. So all these things, if you merge, you can also write it as modulus of z e to power iota theta. So if you expand e to power iota theta in power series, that will be 1. Well, initially you can write 1 plus, if you know na, e to power x को कैसे लिखोगे? 1 plus x square upon 2 factorial, so on and so forth तो लिखोगे. So e to power iota theta, if you expand, you will be this, you can write it in this way. So it is nothing but it is, so any of your any complex number, for any complex number, what you need two things. One, define me the modulus of that particular number, and also give me the argument of that particular number. I will define it. So in this sense, it has a vectorial kind of understanding. So बचपन में vectors पढ़ा था ना, for any vector you need the magnitude and the direction. So for complex number you need modulus of z and argument of z. Now the point is this argument is not a unique character. So if I write this particular here thing, what would be argument? It would be tan inverse 1. Let's say if it is 1 comma 1, then you can write tan inverse 1. But tan inverse 1 is not always pi by 4. It can also be written as pi plus pi by 4. Okay. So in order to restrict this multivaluedness, you define something called as the principal argument of a complex number, which we are going to see later on. But right now, I hope till now everything is clear. Okay, till now everything is clear. Okay, I'm only teaching you
sir.
complex
Yes, sir.
numbers. Okay, so right now I'm not coming because I thought ki, not many people are acquainted, and then people don't even understand ki how to draw a complex number. Then there's a problem. So it's better to give 1 or 2 day on these basic things also. Okay. Now, little bit about the properties, or you can say a little bit about properties of absolute value, or the magnitude, or you can say what should I say, modulus of complex number. Okay, little bit about the modulus of complex number. So already we know. So first thing is, okay, so first thing is, if I want to define a modulus of a real number, what it is equals to x if x is greater than 0, and it is equals to, sorry, modulus of x, and it is equals to minus x if x is less than 0. Okay, now the point is this, because in sorry, in complex number you do not have any such ordering, so you cannot have this kind of understanding here. So but otherwise you understand, whenever I write this kind of expression, what does it mean? It means distance of x from 0. One of the other understandings of modulus or can be in the metric sense. In metric sense, I can define modulus of x as a distance of this number from 0. Okay. So in complex number, you cannot have an understanding with this kind of expression. So in general, in real numbers, whenever we define modulus of a real number, the first definition that we think is this. Indeed, it is right, but in complex numbers, you cannot write modulus of z is equal to z if z is greater than 0 and minus z if z is less than 0, because we already know that the set of complex numbers do not have any such ordering property as we have in the set of real numbers. But one of the understandings of this modulus or absolute value is the distance of a real number from the origin. Okay. So distance of real number from origin, you can also write it as modulus of. Am I audible now?
Yes, sir.
Okay. Okay. So similarly, when I write modulus of z, what does it mean? It means the distance of this complex number what sort of complex number? Z. Distance of complex number z from the origin. From the origin. Okay. So if I say, how would I write the distance? You know that if I'm writing this distance, if this is x comma y, so obviously x comma y would be equal to what? X, this particular distance would be equal to what? So you know that this distance would be equal to simply root over x square plus y square. So simply when I say that z is a complex number that is given by x plus iota y, what would be modulus of z? Modulus of z will be the distance of this particular number from the origin, which certainly would be equals to root over x square plus y square. Is that clear? Now, a few properties. If I'm writing that modulus of z is equal to 0, so modulus of z can be 0 if and only if both x and y are 0. Because you know that what is modulus of z? You know that modulus of z is simply x square plus y square ka root over, and it implies that x square plus y square certainly has to be 0. And you already know that x square is always greater than equal to 0 and y square is always greater than equal to 0. So clearly the solution from this would be x equal to 0 and y equal to 0. So both have to be 0. So mod z equal to 0 can be mod z equal to 0 if and only if z is equal to 0. I hope it is clear. Okay. Similarly, you can prove a few more things because you know that by definition itself, you know that if I am trying to find the real z and take the modulus of it, it will be always less than equal to the modulus of z. Because what is modulus of z? After all, modulus of z is x square plus y square ka root over. If y is 0, then there can be equality. Otherwise, the real part of z is always going to be less than equal to the real part of z ka modulus is always less than equal to the modulus of the complex number. Similarly, you can write for the imaginary part. So imaginary mod is always less than equal to modulus of z. Okay, and equality will hold only if the either of the two. Equality holds if either imaginary part is 0 or the real part is 0. So equality will hold only if imaginary z is equal to 0 or real z is equal to 0. Otherwise you can always write that real part of z ka modulus is less than equal to modulus of z, and imaginary part z modulus is always less than equal to z. And a few other properties I think you can write on your own self. These are like z1 into z2 modulus is equals to what? It is equal to modulus of z1 into modulus of z2. And similarly, you can write z1 by z2 modulus is equal to modulus of z1 divided by modulus of z2. And certainly z2 has to be a non-zero complex number. Another thing is there is a sense of linear because of the linearity in the addition. You can write that real part of z1 plus z2, real part of z1 plus z2 is equals to real z1 plus real z2. And similarly, imaginary part of z1 plus z2 is equal to imaginary part of z1 plus imaginary part of z2. Both of these things you have to remember. I mean, these are easy things. You can do it on your own also, but I have written. Okay. What you can do, if I want to write the real part of z, it is simply equals to what? It is simply equals to z plus z bar divided by 2. And if you want to write the imaginary part of z, sorry, if you want to write imaginary part of z, then it is simply equals to z minus z bar divided by 2i. I hope it is clear till now. Okay, so all these things you already know, but I have just written it for the sake of writing it so that you don't get confused. Okay, is that fine?
Yes, sir.
Okay, good. चलो एक क्वेश्चन करते हैं थोड़ा सा. Okay, so if z1 minus z2, if z1 minus z2 bar and z1 z2 are both real, then either z1 and z2 are both real, or one of them is conjugate of the other.